we usually use this kind of notations. For example, if we mean the partial derivative of u with respect to x, we simply write ux. And if we mean the second partial derivative of u with respect to x, we just write uxx. Let's consider some examples of partial differential equations where we can utilize our knowledge about how to solve ordinary differential equations. First example is the following: uxx equal u. This is a partial differential equation. We solve it in the following way. We are differentiating 2 times with respect to x, and we just solve a corresponding ordinary differential equation, which takes the following form: the derivative of u 2 times equal to u. It can be written in this way, and in order to solve such ordinary differential equations, we just write the characteristic equation. Those who have forgotten about this, please consult Kreisig or other literature on this field. And the characteristic equation is very easy to find. It's r squared minus 1 equal to 0. And the solution of this characteristic equation is 1 and minus 1. So when we are finding the solution of the ordinary differential equation, we just write it like this: u equal to a multiplied with the exponential function of the first solution of the characteristic equation multiplied with x, plus b, a constant b, multiplied with the exponential function of minus 1, this characteristic value, multiplied with x. In our case, u is also dependent of y, not only x. So in our case, the general solution for us is this solution. It looks like the one for ordinary differential equations, but note that these constants are only constants with respect to x, so it may be dependent of y. Let's consider a second example. Let's take the partial derivative of u with respect to x and take the derivative of this guy with respect to y and put it equal minus the derivative of u with respect to x. In this case, it's very useful to make this type of substitution. We define a new variable p, which we put equal to ux. And now we see that this partial differential equation can alternatively be written in this way. Just check it out. If you take this guy p and take the derivative of p with respect to y, then we get uxy. And if we take minus p, then we get minus ux. And this is the equation we had. So these two equations are equal. So this partial differential equation may be solved in exactly the same way as an ordinary differential equation. Just divide each side of this equation with p. This is very common to do this method for ordinary differential equations. We divide it with p, and then we get this equation. And the reason for getting this equation is that we now see that the left side of this equation is in fact the derivative of ln p with respect to y. So we obtain this equation. What does this mean? This means that the derivative of this guy equal to -1, then we can take the integral on both sides and get ln p equal to the integral of -1 with respect to y is minus y. And we have to add a constant, and this constant, remember that this constant is not a constant with respect to x, it's a constant with respect to y, so it may depend on x. Okay, so in order to find this function p, we just take the exponential function on both sides, as we have done here. P equal to the exponential function of ln to p, ln p, and this is, we just put this, replace this p by the ln to p by this right hand side, and use the properties of the exponential function like this, and call this guy for c2. The next we do is we now have that p equal to this guy. We have this equation, and we now go back and see what we call p. P is ux. Remember, our original partial differential equation had the unknown u, and we want to find this unknown u. So we put p equal to what we call pu, namely ux, and get this equation. So in order to find u, we just have to integrate with respect to x. And this is what we have done here. We integrate with respect to x. This means that this factor is considered to be a constant with respect to x, and this guy must be integrated. So we call the integral of c2 for c3. And of course we have to add an arbitrary constant which we call k, and this constant is only constant with respect to x, so it may depend on y. So this is a general solution for our original partial differential equation, which took this form.